My name is Allison Somerset. I'm the Executive Director of the Delaware River Greenway Partnership, and DRGP works to preserve and enhance the natural, cultural, and recreational resources of the lower Delaware River in New Jersey and Pennsylvania. Part of our mission is education. Our presentation tonight explores the characteristics of the Delaware River, the geologic history of the river basin, and the impact that humans have had on the river basin over history. Thank you to Pierre Lacombe for sharing his expertise with us tonight. Pierre retired from a career with the U.S. Geological Survey. He's the president of the Geological Association of New Jersey and has a special interest in the use of stone sleepers as precursors to wood ties for New Jersey's earliest railroads. There'll be a time for Q&A at the end of the presentation, but feel free to submit questions as we go along. Preferably into the Q&A section rather than chat, but we'll be paying attention to both. And with that, I'm going to turn this over to Pierre. Thank you so much, Pierre, for being here with us tonight. And
thank you, Allison. So the talk we're going to give tonight is on the Delaware River and the geologic history of river flow in the basin. The whole reason why I developed this conversation was about 10 years ago, 15 years ago at work. I received an email from Burlington. I live in Burlington County, the Burlington County historian, a man by the name of Eric Orange. And he asked me, how old is the Delaware River? And I thought that was a pretty curious question. So I spent a couple of days figuring that out, and I sent him back an email with my estimate of the age of the Delaware River. And I got to thinking about the question, and at the time, the GANG, which is the Geologic Association of New Jersey, we were having a field trip, and usually we go and look at rock outcrops. But New Jersey has got so many urban areas, we can't see the geology in a lot of the urban areas. So I designed a field trip to get on a boat in Philadelphia, the Spirit of Philadelphia, and ride up the Delaware River, describing the geology on either side of the river and below the river and the history of the river. And I got an invitation to give a talk on the same by a group along the Delaware River. And Barbara Ross saw that, and she asked me if I would make this presentation to the Delaware River Greenway Partnership. And I agreed to do that. So I'd like to thank Barbara, and Cindy and Mark have been very helpful in making sure all the parameters are met. So we're going to be covering 4 topics here. The basics of river flow in the Delaware River today, Delaware River flow from 500 to 800,000 years ago during the glacial interglacial cycles, and Delaware River flow from 200 years ago to present during the Industrial Revolution. That's kind of the realm where the Delaware River was actually a river. Then there were precursors to the lower Delaware River Valley, and the Pensacola era river and the Bridgeport era river. We'll be talking about those. And then there were rivers crossing what's today the Delaware. Obviously, the Delaware wasn't billions of years old. It's not even 10 million years old, but the New Jersey coastal plain strata is on the order of 15 million years old to 99 million years old, and the Newark Basin is older, and the Poconos and the Valley and Ridge and the New Jersey Highlands are even older. Then we'll summarize this. I intend to speak for only 45 minutes, and wherever I am, at 45 minutes, I'm going to stop. Just can't keep on talking all night long. So there are 3 sections of the Delaware River today from my perspective. There's down in Delaware Bay up to the Delaware Memorial Bridge is tidal saltwater flow. So that's the southern part of it. And then the section from the Delaware Memorial Bridge to to Trenton, to the where the waterworks are, is tidal freshwater flow. And that's the estuary part of the bay. And then from Calhoun Street Bridge to New York State and into the Catskills, that's a non-tidal freshwater flow. So those are the three parts. The Delaware River program really looks at the lower Delaware River from the Delaware Water Gap down to the Wilmington area. But I'm going to be talking about the whole river coming back and forth. But I will try to focus on the lower Delaware River. So rivers, there's two types of rivers. There's gaining streams and losing streams. And the Delaware River historically is a gaining stream, and that's a stream that gets bigger and bigger and bigger as you go downstream. And almost all streams in New Jersey and Pennsylvania, New York, New England are gaining streams. And streams get water from three different sources. One is rainfall just falls right on the top of it. Very little water gets into the river that way, but some water gets there. Overland flow from surface, so that's storm sewers and streams and rivers that flow into the Delaware River. But groundwater discharge is the predominant source of new water to a stream. So it's all the springs that are along the bottom of the Delaware. And if you walk up the Delaware River at low tide from Philadelphia to Trenton, you'll see thousands and thousands of little springs all discharging into the Delaware River. And that's only in the intertidal zone. If you go underneath the river, there are a great deal more. If you go out to Nebraska, not Nebraska, but Nevada, Utah, those are a lot of those streams are losing streams. So the stream is big in the mountains, but then it gets out into the desert lowlands and the water discharges into the aquifer. So it gets less and less water as time goes on. And eventually the stream disappears and lots of water evaporates, but most of it just discharges into the aquifer. So when we talk about the Delaware River, it's historically a gaining stream, but the rivers of Nevada are historically losing streams. So flow in the Delaware, we gain and lose water today via natural and human-induced methods. So precipitation is always a gaining method. Overland flow and tributaries are always gaining. Groundwater inflow and springs are always gaining. Wastewater disposal is typically gaining. And reservoirs releasing is typically gaining. We have about 13 or 14 reservoirs in our base, and we release water. Evaporation is a loss. Surface water withdrawals, they take water out of the river in Trenton and Philadelphia and about 20 other communities along the Delaware River. That's a loss of water. Groundwater withdrawal, there's lots of communities. Burlington, New Jersey withdraws water from its aquifers, and that water comes out of the Delaware River. And interbasin transfer, so that's where the Delaware Raritan Canal, we take water out of the Delaware River and move it to the Raritan River. So those are the types of losses that a stream can have. So I'm going to be talking about from 500 years ago to 800,000 years ago through the 9 cycles of Pleistocene, glacial, interglacial epochs. So if we look at the Pleistocene glacial epochs, the 9 most common ones, they start about 800,000, 781,000. I'm going to be talking in round numbers today, because for me to deal with 781,000 gets kind of ridiculous. You guys understand 800,000 years, and that's good enough. The last glacial melt left the Montreal area about 11,000 years ago. It left New Jersey about 17,000 years ago. So we'll be talking about those 9 glacial interglacial cycles and flow in the Delaware River. So these are the 9 cycles. The warm era are shown in yellow, and the cold eras are shown in blue. You see, they're all about 200,000 or about 100,000 years old, each one of these cycles, or the duration. So we're living in the recent warm cycle. The last glacial era was the Wisconsin. The last warm era was the Sagamonian. The last cold era before that was the Illinoisan. Then all of these are classified as pre-Illinoisan glacial interglacial cycles. So you have warm glacial interglacial periods and cold glacial periods. If we look at these, the flow in the Delaware River during the warm interglacial maximum, we have tidal saltwater flow and the deposits of the Cape May Formation. Those are in the Burlington, Camden County areas. You can also find them in Salem and Salem, Gloucester, and Cape May and Cumberland counties. Then there's the interglacial mean period, which I labeled B, and it's tidal freshwater flow. This is the section in the Delaware near Burlington County. Tidal freshwater flow flows to the southwest today. It's just flowing out to the ocean, but it's flowing southwest. Then there's the glacial interglacial transition. And in the Burlington County area, it will be a non-tidal freshwater flow to the southwest. And there you see glacial deposits called the Spring Lake deposits. We'll be talking about that a little bit more. And then the glacial mean, that's during most of the cold. And so the Delaware down in the Burlington County area is non-tidal. It's all freshwater and flows to the southwest. And at the glacial maximum, now this is when the glacier is up in the Metuchen area, it's covering most of northern New Jersey. The weight of the glacier depresses land surface. So there's very little flow because this is all tundra area at this time, but there is a little flow during the spring to the northeast to the depressed area where the glaciers are. So if we look at the last 20,000 years, this period, this cold glacial period, there are no humans along the Delaware River before 12,000 years. The Paleo Indians came from 10 to 12,000 years ago. So the Delaware, there's just nobody here at the time. There's no humans. There's obviously animals along here. And then the earliest Indians lived at the start of the warm period. Hence, they were moving in here. Then the Archaic period, 4,000 to 10,000 years ago, is when the Delaware started to warm up, and the depth of the water, the changes in sea level. Today, sea level is 0, but 18,000 years ago, sea level is about 375 feet below sea level. When the Indians first started coming here, it was about 180 feet below today's sea level. And so if you were to look for Indians living along the Delaware River or Delaware Bay, you're going to find that their homes are in Delaware Bay. And so you're not going to find any features up in the upland areas. They're always living by the water, and those areas have been inundated with 180 feet of water. The Archaic Indians, 4,000 to 10,000 years ago, and starting about 7,000 years ago, sea level has only increased by about 8-10 feet during the woodland Indian period from 450 to 4,000 years ago. So this just kind of puts a human perspective. Clearly, the Indians contaminated the Delaware River to the maximum of their capability, but there's only 7,000 of them. So there's not really much contamination going on. The earth could handle that. So if we look at Delaware Bay today, on the left-hand side of this, you can see that Delaware Bay is quite a wide feature. It's 20, 30 miles wide, and it's flooded. But if we go back to the previous glacial maximum, the Delaware was only a couple of 100 feet wide, and all of the area at the mouth of the Morris River, mouth of all the Delaware rivers, they were dry. And so the Indians would have lived along this area right here, and they would not have lived along these areas because they were just too far from a source of water. This would have been a very cold period. You have to remember that there would be no Indians. This is the previous glacial maximum. But if there were people, they would be using the river. However, on the previous glacial maximum during the Sagamonian, or during the periods of the pre-Illinoisan high sea level was 16 feet higher than it is today. So the Cape May Peninsula would have been completely inundated. Many of the towns along the Delaware on Delaware Bay, both the Delaware and the Delaware and New Jersey side, they would be completely inundated to an altitude of about 16 feet today's. So you have this fluctuation going from this to this, back to this, back to this, every 100,000 years. So today, flow today and the previous interglacial means, flow in this area and this area is non-tidal. This area is non-tidal, freshwater flow from Trenton to Wilmington to the Delaware Memorial Bridge. It's classified as tidal freshwater flow. And from the Delaware Memorial Bridge, as I said earlier, it's tidal saltwater flow. The Delaware Memorial Bridge is the arbitrary saltwater freshwater interface. However, during the previous warm interglacial, sea level was 16 feet higher. So this whole section of the lower Delaware Bay would have all been tidal saltwater. This section from here to about Scudder's Falls would have been tidal freshwater. When they installed the gauging station in downtown Trenton in the 1930s, that station was completely non-tidal. Today, it's occasionally tidal. So the tides have risen as a result of the fluctuations due to the glacial interglacial periods. And then the tidal saltwater flow would have been all of Delaware Bay, past Philadelphia, up to certainly as far as Bordentown. During the cold glacial period, all this area is covered by glaciers, so there's no rivers up in here. You have katabatic winds that are coming off these glaciers because the glacier extends from here all the way to Delaware Bay, and not Delaware Bay, Hudson Bay in northern Canada. So the winds that would come off of here were just horrendous winds blowing this whole area. So there would have been no trees in this area. This would have been all dry land. So you can see the New Jersey shoreline in the background, but it would have been dry land out another 60, 80 miles into the ocean. So Delaware, what's today the Delaware Basin, is not really what the basin was during the last glacial period. Sea level was 300 feet lower. So flow direction, when it did flow, would have been downstream to the southeast or southwest here, southeast. But because of the weight of the glacier, that depressed the land here. So flow in this part of the Delaware would have been northward towards the glacial front. It's just So if we take a look at mean interglacial coastline, so we're looking at the surface geologic map of southern New Jersey. And you can see these various colors. They're just different age sediments. And during high tide, or during, not high tide, but during the last interglacial period, all these yellow sediments and light green sediments was where sea level was, the maximum sea level. So you end up with sea level being here. Now I don't include all of northern coastline. I just go up as far as Barnegat Inlet. But this is pretty rough. But this is because we can map these Cape May deposits. These are all the Delaware River as such. This is just when the Delaware was a warm interglacial, the last warm interglacial period. Of course, if we take a look at northern New Jersey, this is again the surface geologic map, mean interglacial coastline. And the glacier came down to here. This area would have all been dry land. River flow would have been to the north towards the glacial depression, and down in this region would have been south. And these orange deposits are deposits that were created when the spring melts, carried phenomenal amount of water, and it would have made this deposits, the spring lake deposits, and it consists of boulders and cobbles. So if you go to the waste management landfills that are over here, they're all sitting on the geology map of Pennsylvania. Doesn't have as detailed geology maps as New Jersey. So, but these orange deposits exist in this area. And if you drive in this part of the county, you'll find large boulders the size of washing machines along the edge of the road. And if you go into other communities, I happen to live in Florence, there's boulder fields down about 15, 20 feet. And they're caused when the glacier melted in the springtime, it would melt phenomenal volumes of water, picking up heavy masses of mud and clay to the point that the river is like a very thin mayonnaise. And so it can pick up pebbles and cobbles and boulders as big as a washing machine, and just wash them down. And that's what you're seeing with these orange deposits. So this would have happened 9 times during the glacial interglacial periods, or approximately 9 times. Not every glacier moved this far south. Some of them moved a little further north. 1 or 2 of them moved a little further south. So at present, this is the present shoreline of New Jersey and Delmarva Peninsula, Long Island. But 11,000 years ago, the shoreline was 60 miles offshore. And 17,000 years ago, when the glacier cut across northern Long Island and across the state of New Jersey, the shoreline was out to the continental edge, and the Hudson River, the Delaware River, this was all tundra region. There wasn't a great deal there were no trees here at this time. There were very few trees here at this time. So that deals with flow during the glacial interglacial period. Now we're going to deal with flow of the Delaware River during major human activity. So from 1823 to 2023, there's nothing magical about the number 1823, except that it's 200 years before now. And this is during the Industrial Revolution. So since the 16, 17, 1800s, there's been many changes in the Delaware River, both in volume and water quality. Groundwater used to discharge from the coastal plain. Groundwater withdrawal occurs now in the coastal plain. Delaware maximum flow during drought of the 1960s. We'll talk about that. The drought-induced increased chloride concentrations in aquifer. The Delaware minimum flow during the drought of the 60s. That caused the New Jersey and Pennsylvania to build reservoirs. Decreased water quality due to human industrial waste disposal. Improved water quality due to DEP, EPA, and DER rules, and our rules. Dredging islands for ferry operations, dredging the bottom for large vessels, filling lowlands of the dredge spoils. So these are some of the things I'm going to talk about. I could go through hundreds of things, but if we take a look at the aquifers, now in New Jersey coastal plain, there's 11 major aquifers. The recharge area, and if you look at water levels 100 years ago, 150 years ago, this area had very high water levels. The water level in all of the New Jersey coastal plain was above sea level. And so flow went from this recharge area and it discharged into the Delaware River. So you had flow lines, the water would fall in here, the water would fall in this area also, but it would flow into and discharge into the Delaware River 200 years ago. But then we started putting in wells for water supply. And we put in hundreds, if not thousands, of water supply wells, industrial supply wells, public supply wells. And they have since made the water levels drop to minus 120 feet below sea level. So what was used to be 50 feet above sea level today is 120 feet below sea level. So sea level, water levels have dropped 170, 180 feet in the past 100 years. And now this flow, which used to go, I'm hoping you can see my cursor while I'm pointing at this, the flow that used to go to the Delaware River now goes to this massive cone of depression, and flow from central New Jersey goes to this cone of depression. And most of the water, because the gradient, the contour lines are very close here, this is the highest gradient, so flow now comes from the Delaware River into the aquifer. So what used to be groundwater discharge to the Delaware River is today groundwater withdrawal from the Delaware River. The advantage of this is you're filtering the water through a couple of hundred, if not 2, 5, 7, 10 miles of aquifer. So the water becomes very purified by doing that. So if we take a look at the Delaware River Basin, historically, this is the outline of the basin. And the basin is always defined by the topographic divide, not the hydrologic divide. So when water flows, surface water flows towards the Hudson River here, flows towards the Delaware, flows towards the Delaware, flows towards the Susquehanna. So this is just surface water. It's not where the groundwater flows, it's only where the surface water flows. So this plot of land right here is giving water to the Delaware River. So when we talk about the Delaware River Basin, we're really talking about just the surface water, not the groundwater component of it. And today, groundwater flow is being withdrawn from this area, but we're also withdrawing water, pulling water from the Atlantic rivers, the rivers that flow into the Atlantic, coastal plain rivers, and that water is now given to the sewage treatment plants that dump it into the Delaware River. So we're transferring water that taking water out of the Delaware River, using it, putting it in our sewage treatment plants, and sending it back to the Delaware water. Delaware River water that used to go to one of the small rivers discharging into the Atlantic Ocean now gets pulled into the water supply wells in the Camden County area, Burlington County, Gloucester County, and then it gets sent to the sewage treatment plant. So you have to deal with where's the water coming from, where's the water going to. If we take a look at, this is a hydrograph of daily discharge in cubic feet per second of the Delaware River just upstream from the Calhoun Street Bridge. If you, all of you have driven over the Calhoun Street Bridge, the U.S. Geological Survey maintains a gauge there. And so during the storms, water, the Delaware River will flow at 100,000, nearly 200,000, occasionally 300,000 cubic feet per second. Most of the time it's in the 10 to 20,000 cubic feet. During the summer, discharge is 1,200, 1,500, maybe 2,000 cubic feet per second. However, during the drought of the 1960s, and that's this low area right here, what happened is this drought caused the saltwater front in the Delaware River to move upstream and not be at the Delaware Memorial Bridge, but rather get to Philadelphia, to where the Schuylkill River discharges into the Delaware and a little further north. And because that caused public supply wells in both Pennsylvania and New Jersey to go salty, the two states got together and they started building a bunch of reservoirs in the Poconos in northern New Jersey. Excuse me, I gotta take a sip. And those reservoirs try to keep discharge in the Delaware River at Trenton above 200,000, 2,000 cubic feet per second, sometimes 2,500, but they do not want that saltwater from withdrawing, from moving upstream. So they release reservoir water during low flow in the summertime to keep flow greater than 2,500 cubic feet per second. So the early 1960 drought, the movement of the saltwater front was from here up to about here. Supply wells in Salem City, Camden City became very salty. And it took the Salem City's wells the better part 60s to the 90s, the late 90s, to go back to being freshwater. The Camden wells came back in about 10 or 15 years. The reservoirs they built to store the water, there's all these different reservoirs. You can go online and see what the name of the reservoirs are. That's not important. The fact is that they built many reservoirs just to keep flow, protect the water supply of Philadelphia, protect the water supply of Bristol, of Salem, of Camden. Another issue was dissolved oxygen in the tidal freshwater Delaware. So along the Delaware, there's these mile markers that the Army Corps of Engineers put out. So 60, 70, 80, you know the number system as well as I do. So Trenton is about at 130. So from Newcastle, Delaware, about mile marker 60, to Trenton, mile marker 130, in the 1967, the oxygen concentration south, downstream of Newcastle, Delaware, was on the order of 4 milligrams per liter oxygen. But once you got to Wilmington, when their sewage treatment plants were discharging, the oxygen concentration dropped down to 2 or less than 2. The same was true in southern Delaware County. mile marker 90, which is where just downstream of the Schuylkill River, mile marker 100, which is near the Pennsauken stream. And then you start getting clean water again as you get up to Trenton. So fish, the catadromous fish that, and the diadromous fish that try to migrate up in here, they can't swim through 35, 40 miles of oxygen poor water. They just do not have the ability to do that. And so as a result, you and I got together, we asked the New Jersey DEP, the New Jersey DER, the US EPA to do something. Well, these organizations didn't even exist in the 1960s, and they pushed by 1980s. They had to build sewage treatment plants. They had to make regulations that industry and that communities couldn't discharge wastewater. And by slowly doing that, they brought the oxygen level in the Delaware River from being deadly to fish up into livable for fish, and the migration has begun to come back. This red box right here, during the winter time, concentrations are on the order of 10 milligrams. In the summertime, because warm water doesn't hold as much oxygen as cold water, so this is summertime, and the wintertime water is the W up at the top. So there fluctuates even within those two parameters. But we, the US EPA, the NJDEP, the Pennsylvania DEP, and the Delaware River Basin Commission, they all encouraged this change to change the water quality. So this is just showing over time from the 1960s to the 1980s. By the time the 1980s, sewage treatment plants started getting built, oxygen concentrations increased, and now we're sitting for low oxygen at 4.5 or 5. Bald eagles, a very similar phenomenon. Now that you have fish in there, the bald eagles have something to eat. They're piscivores. And so in the 1990s, and so the population of bald eagles increased in Pennsylvania, New Jersey, and New York. And blue crabs, the same thing. They were able to survive. So it's not only fish, it's other animals that ride on this need for oxygen. This is Camden, this is downtown Philadelphia. There used to be rather large islands between these two areas, Windmill Island being particular. Those have all been removed. So we have removed lots of sediment that was in the river. If you go downstream, this area is where the airport is today. And so Tinicum Island still exists, but Billings Island, Hog Island, Fort Island, this is where the fort is, Fort Monmouth. All these islands have been removed or filled. The back bays behind them have been filled in. And as a result, you've made the river go from a 3/4 of a mile to a 300, 500 foot wide river. So these are just physical changes that we've done to the river in the past 200 years. They've also dredged a channel. And so in the 1880s, the natural depth of the river was about 17 to 24 feet deep. They started dredging, and they brought the depth of the river down to 26 feet about 1900. And then they brought it other areas. Obviously, this goes to 30 feet by 1900. This scale is kind of wonky in that sometimes a decade is the same length as a year. So this is 1 year, that's 2 years, 10 years. So, and then today, or 1924, after the onset of World War II, they got the Delaware down to 40 feet below sea level. So they had dropped it from about 20 feet to about 40 feet, and they started dredging the channel to 45 feet in the last decade, 2 decades. So the Delaware Channel has deepened the river significantly. And so this is what the river would have looked like 200 years ago. And today the river is very, very much twice as deep in the channel. So you start hitting bedrock, so the discharge has to come along here and here. There's lesser and lesser discharge here. There are other issues in that recharge from here is now easier. And there's issues with friction in the river, and high tide was much lower 250 years ago. Now that you have a much deeper, you have less friction, so the tides have gotten much higher in the northern part of Burlington County. So dredging operations over the last 30 years, I'm not going to read this whole thing because I've got to be finished in a couple of minutes, but they've dredged and the dredged. And this brown land right here is all landfill. When they dredge the river, they have to put the sediment someplace. So this area used to be water filled, and now it is landfilled. And so these were the breeding grounds for a lot of fish because it's warm, nutrient-rich wetlands. And now they are filled in with sediments from dredging the Delaware River. And then we harden the shoreline by putting riprap along it. The tides are much higher. So what used to be a sandy beach is now a gravel beach. We put this corrugated steel in here, and massive boats. When those boats, they create big wakes. Those wakes wash the shoreline and wash away the fine sediments, leave behind the coarse sediments. So the precursor to the lower Delaware River is a Hudson-Delaware River system. This is rather quickly. From 4 to 11 million years, the Pennsauken-era River and the Bridgeton-era rivers. So this is the Hudson-Delaware River, and it flowed from the Hudson across northern New Jersey. And the upper Delaware was just a tributary to the Pennsauken River. And so this was a very wide river, and you can see it on Stanford's map. And the Delaware, this part of the Delaware is just a river, and this section is now deposited. And this is the Delaware River Basin. So this area is clearly from outside the Delaware River Basin. And this area is outside, but this former river had a much different river basin. And this is it for the whole thing. So it would have been flow coming down here, and the Delaware just would have been a tributary to that. The same is true for the Bridgeton-era river flow. This is Bridgeton fluvial plain. And here is the Bridgeton river system. And again, the Delaware was the upper Delaware was a tributary to the Hudson-Delaware system. And here is the Delaware River Basin laid on top of it. And here is the whole basin with the Bridgeton Formation sitting on top of it. And these are maps showing that the flow, the older sediments in the Bridgeton Formation are in northern Atlantic County, and the youngest sediments are in northern Cape May County. So we're going to look at Miocene, and this is all the New Jersey coastal plain sediments from the Potomac, Raritan, Magathie up to the Cohansey. And there used to be rivers that would flow across, and they would create mountains like, I don't have enough time to go into the whole, but think of Batstow and all the iron mines that were there because of the flow of the discharge of groundwater. There were bacteria that used that dissolved iron to create ironstone. The tops of the mountains are all ironstone. So the tops of the mountains, that being Clarksburg Mountain or Mount Holly, Arnie's Mount, those used to all be river tops, river bottoms, but because of the ironstone, they became mountain tops. It's convoluted thinking, but it's the way things happen. This line right here, the intercoastal plain, the outer coastal plain, this is just the line that separates when the dinosaurs were killed. There were dinosaurs during this green era. There were no dinosaurs during this orange era. In the New Jersey coastal plain, there's all these clay layers, thick clay layers, and sand layers. So there's 11 aquifers, the Kirkwood, Cohasset, the Piney Point. These are out in Cape May County and Atlantic County, Vincenttown, Winona, Mount Laurel, Englishtown, the PRMs. And so these sand units, sand was brought in from rivers coming off of central New Jersey. And to go into, but the Delaware didn't exist at all. These are all flow coming from west to east. Let's go. And then if you look at topographic maps of the bedrock surface in lower Bucks County down near Philadelphia, you'll see river drainages within the top of the Wissahickon schists. And these are the former rivers that flowed perpendicular to the Camden and Amboy when the Potomac sediments were being deposited. And here in the Florence, Bordentown area, these are the river channels that existed. And these are the ancestral river channels that are in the Tullytown, Bordentown area. So this is just flow perpendicular, sometimes parallel, but flow perpendicular. And if we look at the Triassic deposits, so that's this light green color up here. That's when the Atlantic Ocean split open, and these were filled by rivers coming into, because this was a whole mountainous area, this was a whole mountainous, and this was a fracture, so this was a bunch of freshwater, saltwater lakes, and those deposits were during the Triassic and Jurassic. So those are the red sandstones and the brownstones of New York City, and when you're in any of the communities, the river communities with the red sandstone buildings. The Carboniferous, so the Paleozoic, 300 to 500 million years ago. Now we're talking about Africa up against us, and sediments are flowing in from this and flowing in from here. And as a result, you end up with lots of deposits in here. And then you go for the Cambrian and Proterozoic deposits, 500 to 1,000 million years ago. And this is North America, and flow is coming off of this craton. There's no trees, there's no plants on this, so this is just continued flow. And so the flow would have been in this direction, and obviously this was another part of the world, but the flow would have been perpendicular to Delaware. It's not even thought of at this time. So this is the summary. In this era, we're dealing with a lot of fluctuating between tidal, non-tidal, freshwater, saltwater, regulated flow, dredging, treated waste. 100 years ago, there were open sewers, but today we've got that all treated. 6,000 years ago, the Delaware was non-tidal, freshwater. 17,000 years ago, there's permafrost. 100,000 years ago to 1.5, we're dealing with saltwater. We're dealing with very large rivers. And then we're going to the to the Miocene and Cretaceous. This is the New Jersey coastal plain, many rivers. The Triassic, we've got sediments filling in, the Permian, Silurian sediments filling that. So that's all. I'm gonna, now I've overrun by 10 minutes, 5 minutes. I just would like to thank Barbara for asking me to do this, and Cindy and Mark for setting up all the electronics. If you have any questions or comments, please ask.
Yes, thank you very much, Pierre. Very interesting. So I'm Cindy Kunis. I'm projects coordinator with Delaware River Greenway Partnership. We have a couple of questions. One was asking about having a recording. Yes, we will have a recording on our YouTube channel. I will post that channel link in chat in a minute. So we have one question about what are some of your favorite books about this topic?
I would have to say the best book on the geology of New Jersey for the layperson is Roadside Geology of New Jersey, written by Dave Harper. And I think that's the simplest book. The New Jersey Geological Survey has a couple of superior geologists, Scott Sanford in particular. He's very good. And Pete Sugarman also is very good. So things that those men have written are very, very helpful.
Wonderful. All right. So yeah, we have a couple more coming in. How did and when did the water gap form?
Well, the Delaware River used to be at a much higher, and the answer is I don't know. But the Delaware River used to be much higher, and it eroded down, and now it's stuck in its valley. And once it hits the top of that ridge that it's running through, it just starts to erode down that valley, and it just keeps on eroding because it doesn't have an alternative.
Another one is the same history for the Hudson River.
Excuse me?
They're asking if it's the same history for the Hudson River, or maybe similar history.
The Hudson River is, if you take the Hudson River and you follow it north, you come to Lake George, Schroon Lake, Lake Champlain, the Richelieu River, and then you get to the St. Lawrence River. And that's called Logan's Line. And Logan's Line is a fault. All the rocks on the west side, the Catskills, they're all sedimentary rocks. The rocks on the east, you get up the Champlain Valley and you have the Clinton limestones and the Potsdam sandstone. Everything on the west side is all metamorphosed. So that's a suture line. And so that river has been stuck in that juncture between the flat-lying sedimentary rocks to the west of the Delaware, west of the Hudson, and the metamorphic rocks to the east of the Hudson. So I would have to say it hasn't got the same history in that it's tectonically formed, whereas the Delaware is not as clear-cut tectonically formed.
And another question about the water gap. How thick was the most recent glacier at the Delaware water gap?
Again, I don't know the answer, but I'm going to say it covered the New Jersey highlands by at least 1,000 feet. And let's say the Delaware water gap is 250 feet deep. I don't really know how deep it is, but I'm going to take a guess, in excess of 1,100, 200, 300 feet.
Was the west side of Delaware River less affected than the Jersey east side?
Less affected by what?
I don't know. If that was your question, please rephrase it in the Q&A and I will get back to it. Let's move on to another one. So the big boulder in places like Amico Island Park are from upstate New York?
No. Amico Island's an artificial island. Those boulders are from dredging the bottom of the Delaware River.
Given that there have been glacial periods and interglacial periods over hundreds of thousands of years, and given that over recent geological time, sea level hasn't risen much, why the fuss about global warming today and predicted sea level rise?
Please don't confuse me with somebody who doesn't believe in global warming. So I'm going to answer this question in, can I have 3 to 4 minutes to answer it?
Absolutely.
Okay. Okay, you and I are very comfortable with the day, the month, and the year. These are celestial cycles. The day, the Earth rotates once on its axis. The month, moon travels around the Earth once every month. And the year, the Earth travels around the sun. And these cycles cause chemical, biological, and physical changes on the Earth. I anticipated this question, obviously. And so there are other, and so the chemical changes during the day, oxygen is made. At night, oxygen is not made by trees. Flowers bloom during the day. The Earth gets warm during the day and it's cold at night. Flowers close up at night. The moon traveling around the Earth, the tides cause breeding grounds for animals. The migrating birds travel by the moon. The horseshoe crabs lay their eggs by the moon. So this chemical, biological, and physical changes, high tide, low tide, are real cycles that affect us. Women's reproductive cycles are a lunar cycle. In the year, the chemical, biological, apples get produced in the fall time, sheep are born in the springtime, the Earth gets cold in the wintertime and hot during the summer. So these cycles are very, very important in controlling the Earth. There are other cycles, whether the Earth travels around the sun in a circular or an elliptical pattern. I'm going to back up a little bit. The Earth is a very complicated system, and to blame global warming on a very simple solution being greenhouse gases is an error in judgment, and it's unfortunately perpetuated by a group of people. It's caused by a number of intertwined effects. I want to set that up. So the eccentricity of the Earth is on a 100,000 year cycle. Whether the North Pole dips at 27 degrees or 22.5 degrees, that's on a 40,000 year cycle. And whether the North Pole points towards the sun or away from the sun, that changes on a 20,000 year cycle. And so these various cycles, much like with the tide, you get low high tide and high tide, and neap tides, and all these different tides. You get these various cycles that affect the chemical, biological, physical, and geologic Earth. And you kind of have to think of these cycles, the precession, the obliqueness, and the eccentricity, all impact. And so when you're looking at this feature right here, you're going to see cliff faces and slope faces, cliff faces and slope faces, cliff faces and slope faces, the dry periods and the wet periods. And these are Milankovitch cycles. When you look at the New Jersey, the Triassic Basin, you're going to see black deposits and light deposits, black deposits and light. These are Milankovitch cycles. And you take a look at this and these patterns right here, which look sort of like wood grain in a tree. And obviously tree rings are a celestial cycle. These are those 100,000 year cycles that you're seeing in the geology of this area. So global warming is caused by greenhouse gases. It's also caused because this whole area used to be forested. Now this whole area is urban, this whole area is suburban, and only this area is forested today. So land use changes have altered it tremendously, and all the gases that we've given off. So it's a combination, in my opinion, and I don't share this with a lot of people, but it's an opinion that it's a Milankovitch cycle, it's a greenhouse gas cycle, and it's a land use cycle. It's not a simple one, you solve greenhouse gases and you've solved all the problem. The second part of this, I don't know whether I want to go into it, but you've heard the expression that the statistically, do you know who are the best readers in kindergarten? Statistically, it's the children with the biggest feet. And that doesn't seem to make a lot of sense. And it doesn't. It's not the children with the biggest feet that are the best readers in kindergarten. It's the oldest children have the biggest feet, and the oldest children are the best readers. So it's misinterpreting data. And so when we say greenhouse gases, when I was born in the 1950s, the population of the Earth is 1/2 of what it is today. So now I'm philosophizing, and today the population of the Earth is about 8 billion people. It used to be 3.5 to 4 billion. So we just have an awful lot of people on this Earth. And trying to solve a population problem is a much uglier problem than trying to solve a greenhouse gas problem. I've done enough on answering that, so I'm sorry. So this is the Milankovitch cycle. So we're getting warmer, but it's been very, very warm in the past. And these very warm periods where sea level was much higher.
Thank you for that. How did Crosswicks Creek get formed?
How did Crosswicks Creek
Get formed?
Well, you have to envision, now we've got a valley that's 400, 500, 600 feet wide, but we have a stream in it that's only 20 feet wide. How does a 20-foot wide stream form a 400-foot wide river? And the way that it does it is it used to have a great deal more water in it. So during the glacial cycles, when there were spring melts, spring runoffs, it would erode that river very, very dramatically. And as a result, you have an undersized stream in an oversized valley.
Great. I think that is it for questions. Anybody have a last minute one they want to get in the Q&A? All right, then. Thank you very much, Pierre. That was very interesting. Greatly appreciate your extensive knowledge on this subject. And I believe everybody else did too. So thank you.
You're very welcome.
I guess that is it, everybody. Thank you for attending.
Thanks, Pierre.
You're very welcome.
Have a wonderful rest of your evening.
I will do that.
Okay.
Okay. My best.